Hello. Can you hear me, everybody over there? All right. Welcome to our annual Hassan Distinguished Lecture. And I'm Srinath Ikar. I'm the Department Head of Mechanical and Aerospace Engineering at NC State. And I'm very glad that many of you can join, not only in person, but it is on, but maybe I'm not too close enough. Also people online joining us today to attend the lecture. Again, thank you for joining. This lecture series was created by Professor Hassan, a longtime faculty member in our department. He was here for 56 years and more. Unfortunately, he left us in 2019. Dr. Hassan was a legend in his field and very well known, and has graduated a lot of alumni in our department and has had a major impact on our aerospace program. And he continues to, because he's also created, before he passed away, he created the Hassan Distinguished Professor, and we were excited last year to have finally somebody in that role, Dr. Farhan Gandhi, who unfortunately cannot join us today, but Dr. Farhan Gandhi came to us from RPI, and he works on urban air mobility, VTOL aircraft, and he's our first Hassan Distinguished Professor in Aerospace Engineering. Um, in addition to that, Dr. Hassan also set up this lecture series, and and he used to be front and center for till 2019. He would be here asking questions and getting involved. It was great to have him involved, and I'm glad that we are continuing this. And all thanks to that, for that, with our alumni, also his son, Dr. Basil Hassan, who is continuing the legacy of Professor Hassan in this. So I'm going to invite now Basil to say a few words and also introduce our speaker. And after the talk, we will have question and answer session, and then Leslie will be here to have informal chat, and then we'll continue with the rest of the program after that. Thank you. Basil.
Well, good morning, everyone. As Srinath said, my name's Basil Hassan. I'm from Sandia National Laboratories, and I'm here to welcome you to today's event and introduce our speaker. Reminiscing a little bit, I entered as a freshman 40 years ago this semester, so it's quite a long time, and I'm really excited to welcome you to attend this lecture. As Srinath mentioned, it's been going on since 2015. My dad came here in 1962 from Virginia Tech, and he followed former department head Bob Truitt to come down here and help establish the aerospace program in 1962. And as Srinath said, he roamed the halls for more than 56 years, both in Broughton and in EB3. I'd really like to thank the current and former faculty, the students, friends who were all instrumental in helping to set up this lecture. As Srinath mentioned, he passed away in 2019, shortly after he finished phase retirement. And we've had a really great set of speakers who have come to talk to us over the years, including people from the Smithsonian National Air and Space Museum, NASA, Honda Jet, the Jet Propulsion Lab, and Boom Supersonic. If you want to learn a little bit more about the details of my dad's career, I will refer you to the program, but this place really meant a lot to him, and the aerospace program was something that he had his hands in creating, and I think that he really was invested in the success of the program. He was invested in the research that was being done here, but more importantly, the success of his students. I'm really gratified to see several of his former students here today, and I'm sure there are some online. This morning, I'm delighted to introduce another distinguished lecturer in this long line of speakers, who is a colleague and a friend of mine, Leslie White, who is a senior principal aerospace engineer and department chief scientist at the MITRE Corporation. Center for Integrated Transportation. Dr. Whites received her BS in Mechanical Engineering in 2002 from SUNY Buffalo, and her master's and PhD degrees in Aerospace Engineering from Texas A&M in 2005 and 2009. She conducts and leads impactful research in the areas of advanced avionics for next generation concepts, including concept development, design, trajectory modeling, and performance analysis. She's led several important projects related to integrating space launch, reentry vehicles, and advanced air mobility operations into the National Aerospace System, or the NAS. Leslie was recently inducted as an AIAA Fellow and has been a long-term leader within AIAA's leadership, currently serving as head of our Technical Activities Division, a job that I had the pleasure of holding. I first met Leslie about 20 years ago when I was on an advisory board at Texas A&M, and she was a graduate student there. She made a strong impression on me at the time, and I knew that she would have a really great career. I started to follow her again during our time in AIAA when she was chair of a technical committee, and I've really been able to see her have great professional success and grow in her career. As I was reviewing her nomination for AIAA Fellow last year and seeing all the great work that she had done, I instantly thought that she would be a great speaker for our event today, and luckily she accepted the invitation to come talk to us. As you will hear, the network of capabilities that manage our air traffic control system, they're complicated and they're intertwined, and as we add new entrants into the airspace, unmanned aerial vehicles, space launch vehicles, and other things, it just is going to make it that much more complex. So today, Leslie will hopefully tell us a great story about some of the advances and the challenges that are happening here. For those of you who are students in the audience, I would really encourage you to follow Leslie as somebody who can be a great role model. She is to be both admired and mimicked in how she's conducted her career. And while I know she's got a lot of runway left in her career, she'll continue to make great, impactful contributions, and she will be a role model for future aerospace professionals. So with that said, please join me in giving Dr. Leslie Whites a warm Wolfpack welcome.
All right, can you all hear me? Great, thank you so much. Wow, that's a very overwhelming introduction, Basil. I just want to say thank you again for the invitation to speak, and thank you to Srinath for supporting the visit as well. And I also wanted to say thank you for the invitation to the Hall of Fame induction last night. It's really inspirational, and I came away overwhelmed with just the impact and the work that this department is doing. And what it made me feel like is students have so many amazing options from the universities in this country to choose from, and it makes me really positive about the future and the opportunities. It's a really exciting time to be in aerospace and many of our other technical and engineering fields, and so I walked away just feeling really excited. And also I got to learn about your dad more from the remarks from many people. It sounds like he was tough, but it also sounds like he cared a lot about his students, and everybody was better for his teaching and his efforts. So thank you again. So as Basil noted, I want to talk to you all about the challenges in modernizing and integrating new entrants into our national airspace system. I'm not going to do a deep dive in any one technical topic. I want to give a bigger picture perspective on these challenges. And in fact, I don't even think some of our biggest challenges are technical in nature alone. I think there's a lot of other political, financial, and what we call socio-technical barriers. And so I'm going to talk about some of the technical work that we're doing in the context of those challenges. And I hope you take it as inspiration. I think, you know, the event last night, but also even the opportunity to put together this presentation to come talk to you today, I come away thinking how exciting that we get to work in this area where we're problem solvers and we get to work together to tackle these really difficult challenges. And sometimes it's difficult to see progress just from a day-to-day perspective where we're all drowning in email and meetings. And so putting together these presentations allows us to take a step back and really see what progress has been made. So it is an exciting time. First, I want to tell you a little bit about MITRE. It's a unique place, and want to give you some context for the type of work that we're doing. So MITRE is tackling complex challenges. We are a not-for-profit organization that's working with government agencies and public-private partnerships with a mission to solve problems for a safer world. So really working in service to the country. We're applying systems thinking to solve complex problems, and you'll really see the interdisciplinary nature of the work when I talk about some of the federally funded research and development centers that the MITRE Corporation manages. So we have 65 locations worldwide, including one in Raleigh. I don't know if you all know that. There are 20, I looked this morning, there's 26 MITRE employees assigned to the Raleigh site. So they might not all be there on a daily basis, but there are 26 employees working in this area. And actually I looked, there's 46 employees that have NC State listed as one of their degrees. So we have good representation within the organization from this university. So we currently have over 9,000 employees. Real quick, going back to that locations worldwide, a lot of different locations in the US, but there's also a lot of strategic locations around the world. Partnering with our government sponsors in places where we have DoD presence from the US military. And we've been around for 65 years, and you can see we do patents. Even though we don't build products, we are often protecting intellectual property for the benefit of the government and those who might be building things that benefit the American public. So MITRE operates 6 federally funded research and development centers, or FFRDCs, on behalf of our government agency sponsors. The very first one was the National Security Engineering Center, so that was the start of the MITRE Corporation. That is our largest body of our work program. But the Center for Advanced Aviation System Development, or CASD, that's the center that I work with, is working with the Federal Aviation Administration, and that came in 1990. And since that time, we've had 4 more FFRDCs. The National Cybersecurity FFRDC works with NIST, so the National Institute for Standards and Technology. The Health FFRDC works with a number of government agencies that touch on health, so Health and Human Services, Center for Medicare and Medicaid Services, and others. There's also a Homeland Security Systems Engineering and Development Institute. And then the Center for Engineering Modernization, again, works with a number of agencies, including Department of Justice, Department of Commerce, Internal Revenue Service. So you can see that there's quite a varied amount of work and government sponsors that we're touching on. This provides us kind of a unique vantage point in terms of FFRDCs, in that we really do see a cross-government interdisciplinary nature. And often some of these challenges require a cross-government perspective, and so we can kind of draw from the expertise across the company to solve some of these challenges. So a little bit more about CASD, working with the Federal Aviation Administration. We have a couple of key role areas in terms of strategic advisor. We are working with the government sponsor to make data-driven analysis and recommendations. We are mission focused. We are working on behalf of solving the problems that the FAA has. Our goal is to always provide objective insight. So we're not trying to make money, we're not trying to build products, but rather give the right answer. And often that answer has to come in the context of the barriers and the challenges and constraints. We're an innovation partner, so we are trying to accelerate new technology and operations. We are trying to move scientific discoveries into practice, and also trying to think outside of the box. So what are some of the game changers or the transformational solutions? As an integrator, we're thinking across the FAA lines of business, and how do we integrate systems? How do we get the organization connect parts of their organization. As a smaller organization than our government agency sponsors, we're often a little bit more agile, and we can help them make connections that they might not have the right contacts for. And then also looking at those whole of government solutions, that having this breadth of government sponsors we work with might offer interesting perspectives that would be difficult to see from inside those government agencies. And then system of systems engineer, looking at the entire enterprise, so all the systems that the government manages, being rapid in our responsiveness, and then providing institutional knowledge across even several decades. We have people that have worked at MITRE for 40 plus years, you know, just like Basil's dad stayed a long time and he built that institutional knowledge. He knew how to get stuff done. So we have employees that have that similar long-term knowledge. So a couple areas are differentiated value. We're helping envision the future. We also, a big key to that is the pioneering data analytics. So we have access to a lot of data on every flight that happens in the US National Airspace System every day. So you can imagine the data analysis opportunities and what insights we can gain from that. And then again, that accelerating operational integration. So in terms of our areas of expertise, and so this is something for the students to think about, certainly systems of systems engineering. So how do systems need to integrate? How do you analyze those systems? Mathematics, computer science, modeling and simulation. So you can see these touch on often a lot of different engineering disciplines. Big data analysis and fusion. We also have economists that we work with that do economics modeling, and then operational integration. So we also have a lot of air traffic controllers and pilots that we work with to help make sure the systems and the analysis we're doing is grounded in an operational reality. And then we have a number of laboratories that we use for our research. Key to that is our integration, demonstration, and experimentation for aeronautics, or IDEA lab. We have several prototypes of air traffic systems. So you're seeing in the picture, we have a tower simulator. So we have an out the window view. They can represent any, I shouldn't say any, many different airports. So they could bring that up and simulate what we call decision support tools to the tower controllers. And you can do experiments, data collection activities with those prototypes. So now let me get into the heart of some of the challenges, now that you have hopefully a better sense of the type of work that MITRE does. So air traffic management is a difficult domain to break into. There's so much lingo. So I'm going to try and give you the 101 slide at a glance on a single slide, and hopefully that gives you some background for the rest of the presentation. So you can kind of think of air traffic management as a three-phased perspective. So strategic traffic flow management is where we're looking at a high level at the entire continental US. What are the traffic demands that are happening? This can happen up to a day in advance. Sometimes for events like the Super Bowl that we know are happening, we know there's going to be significant demand changes or shifts. They also have plans for ski season, so all the demand going into Denver, for example. And so the Air Traffic Command Center in Herndon, Virginia, is where a lot of the strategic traffic flow management is centralized. And so they talk about what is the big plan to deal with what we call the demand capacity imbalances in the national airspace. So, and this happens too with weather. So we have a snowstorm coming, we have a hurricane. How are we going to deal with this so that it's the least disruptive to the airspace, and then also so that we can quickly recover from the disruption? At a lower look-ahead time level, we do tactical traffic flow management. So this might be in a region of the country. We have a sense of the arrival traffic. There's this, local weather that has to be managed, whether it's thunderstorms that flights have to be routed around. And this is used to efficiently manage flights in these high-density environments. So when you have maybe merge points or you have squeeze points where you're trying to get air traffic around some weather, for example, they're helping to manage that plan. And at the lowest level, but probably the most important, is separation management. So this gets into a sector of airspace where you have an air traffic controller controlling the individual flights. They're telling them what speeds to fly, if they have to route them, or what we call vector them, so they can absorb time because they're too close to another aircraft, or they're changing altitudes of those flights. Their primary goal is to not have metal touch metal. And in fact, there's, that it's very bad if that happens, obviously, and there's separation requirements, so distances and altitudes that they have to keep aircraft apart, and that is their primary job. And it's stressful, and they do a great job doing it. And so you have decreasing uncertainty of what is actually going to happen as you go through these phases of flights. And we work on all aspects of this air traffic picture. And so, with each of these phases, these actions, there's automation systems, there's surveillance systems, communication systems that support the operation. And then if you haven't gotten the sense already, there's a lot of humans involved in the decision making. So I think as engineers, we're often like, let's just automate everything and get the humans out of the loop. This is the opposite of that. There is automation support to help inform the humans what they should do, but ultimately the humans are making the call, and that actually provides a lot of resilience to the system. So if we talk about the characteristics of the National Aerospace System, it's a connected network of airports. As I mentioned, the human operators and decision makers are overseeing those operations at those different scales I just talked about. So the macro, looking at the entire national airspace, down to the individual sectors. It's a complex socio-technical system, which means you've got humans in the loop using automation that are driven by policies and rules and culture of what they can do and when. And so that in itself makes it a very complex system. And it's in fact intractable, so it's difficult to describe at any given one time due to its complexity. So we have continuously evolving capabilities as new capabilities and automation are either added to the system or are even changing as new features are added. And then there's new procedures being added. And so what's interesting is when you combine these complex integrated systems, sometimes they can cause what's called emergence, where you have outcomes that were not predicted because you didn't fully integrate the system, or you didn't test the integrated system in a way that these outcomes would happen. Now, the good news after all of that is that, we would say disruptive events can result in these operational inefficiencies. As you know, the National Airspace System is incredibly safe. So at the end of the day, we do get frustrated with inefficiencies, but people live. So you might have delayed or canceled flights, but those are some of the inefficiencies, in addition to ensuring safety. Our safety objectives continue. That's a lot of the work that we do at MITRE. So safety in the national airspace, I've mentioned it already a number of times, but anytime you introduce a new capability or operation to the national airspace system, there is a safety management system process that gets applied. This is well documented, and you can look it up. This is Air Traffic Order 8000.369C. It's available publicly. So this defines the process that you must go through to identify hazards and then mitigate those hazards. And the system has to be shown that the probability of a midair collision is less than 1 times 10 to the minus 9. So that's 1 with 8 zeros preceding it. And so the way we think about mitigations are kind of like a Swiss cheese model. So you want to make sure that you have enough mitigations in place that even if you fail one of the mitigations, there's enough other mitigations that your likelihood of getting to this midair collision is very, very, very small. And so that's why, I think safety is the overriding priority, and that is why it's difficult to affect change and to change things quickly. But I think if we were all to step back, we'd say, yeah, I think we're pretty happy with the safety focus of the FAA. So where are we going in the future? So one of the big goals is enabling safe, efficient, and equitable operations for diverse users. So we have these new entrant operations that Basil mentioned in the introduction. Urban air mobility is a hot topic, so air taxis. We have small UAS doing package delivery or cargo delivery. We're starting to see more interest in supersonic aircraft and managing those operations, and then space launch and reentry operations. And then on top of that, we have our legacy air traffic operations, so both commercial air traffic as well as general aviation. So all of that has to work together. Some of it you can see from this picture, they are operating in different regions of the airspace, but there is an element of having to integrate those operations effectively. So as part of this modernization, the FAA has put out a vision for this future information-centric national airspace system. And so there's an idea that you have this ubiquitous information that allows everyone that's involved, all the stakeholders, to coordinate and collaborate. And so with real-time data, can we improve decision-making? And then also that continuous focus on safety, there's an opportunity for prognostic safety monitoring. So you have all this data you're collecting about all the operations. Can you identify a concern that needs to have a mitigation in place? And so there's great opportunities with all this data, but of course, all of this has to be defined and systems built to enable this. And on top of that, it's a challenge working across all the various stakeholders to make sure this data can be shared. And so right now, the FAA is defining those future infrastructure needs. So we have communication, navigation, and surveillance systems that exist today, but may have to be modernized. We want to make sure we have resilient systems. And then there is a big evolution, I'll talk about this in a little bit, around software architectures and how we do software. So we're moving, of course, away from legacy systems where you have, hardware servers, operating in the facilities to cloud-based architectures. So software engineering is really evolving quite heavily in how it can support this evolving NAS. So I'll talk about a couple of challenges here. These are, I would say this list of challenges are some that I've encountered in my career. It by no means is a complete list, but I want to give you a sense of the big picture challenges and some of the challenges we're dealing with every day. So for one, customizing automation or bespoke automation for some of the unique aspects of the air traffic operations is a big challenge. And so the en route air traffic centers are divided into 20 en route air traffic control centers in the national airspace. So you can see them in the picture on the right-hand side. And there are unique aspects to each of these. So Albuquerque Center, for example, we do a lot of work with Albuquerque. They have some lower traffic densities than, say, you never try anything out in New York. Like, just, no. That's the last place you go, right? Because it's really challenging. But they have some very unique challenges because of their densities. And then Seattle even is interesting because, you get up into the Seattle area and they have some interesting geographic challenges and that prevent you from doing certain things. So there's unique considerations in every center. And so we design the air traffic automation to be adaptable for these unique operations. And one of the systems that I've spent a lot of time working on in my career is called the time-based flow management system. And this system actually predicts trajectories and estimated times of arrivals and then schedules aircraft at different points in the airspace. And this gives the air traffic controllers decision support information so they can efficiently manage the flight. The adaptation document that tells you how to configure the system is 1,800 pages long. So good luck learning that, right? And so it's a very complicated system. And so we've been thinking about, how do we develop both flexible but cost-efficient systems? So we want to avoid mass customization, and we want to develop common services that support different automation platforms. And this problem, in fact, in 2014, Dr. Scott Ferguson and I, who we went to undergrad together at the University of Buffalo, we had lunch at the AIAA Aviation Conference, and we talked about this particular problem. How can we balance? And actually, I don't have it on the next slide. How do we balance this mass customization with a cost-efficient system? And so we've talked about, applying some ideas in the design engineering field, and so this might be an opportunity. But this is a huge challenge for us. The way MITRE has worked on it, and forgive some of the lingo and the terms, but not only is the number of parameters very complicated, and the length of that document very complicated, but you really do have to set the system up so it works. You have a lot of tuning knobs, but they're not all independent. So you got to think about how you design the system. And so there's the performance-based navigation procedures that the aircraft fly. These are the arrival departure procedures, and this give well predictable and well-defined paths for the aircraft. And then the scheduling algorithms need to take advantage of that, but then also be configured appropriately. So this is an interdependent relationship. So part of our work has been understanding the system relationships that can inform design guidance and process. And then that design guidance and process is complicated. So can we design capabilities that support the user in designing that? And that ultimately, when we use those design tools effectively, can that result in the operational, integrated operation we want? And we're working towards the operational objectives of making sure flights are efficient, staying on their routes, so, which gives the airlines fuel efficiency. We want to make sure the operations are predictable. And so this is kind of the vision that we've had for helping the FAA customize these systems. And so, yeah, so we've been developing these tools and designs for evaluating designs against criteria and evaluating designs in new ways. So this is one body of work that we have in response to customizing automation. Another challenge just comes down to, and you've probably already gotten a sense of it, the diverse set of stakeholders that are involved in operating and evolving the NAS. And so here's a list. There probably are more, but you do have airlines and fleet operators. They're very concerned with how their air traffic is managed. You know, they have a business case they want to meet. You've got pilots who, by the way, might not always be in line with their airline and what they want to do. You have air traffic controllers. You have the folks that work at the command center and do that strategic traffic flow management. You've got the FAA in two roles, both as the regulator of the aircraft and the systems, but also as the infrastructure owner and operator of the national airspace. You could have third-party service providers, and then I shouldn't have put it last, maybe I should have put it first, but we have passengers too. So passengers are a stakeholder in this. And so the challenge is that the stakeholders can have very different and sometimes opposite objectives and don't often understand each other's perspectives. So I think we look for opportunities to bring those stakeholders together. I think at the lowest level, we try and bring air traffic controllers and pilots together so they can have those moments where they say, oh, that's why you do this thing. Okay, I understand a little bit better. So in some of our experiments, our data collection activities, we look for opportunities to bring those stakeholders together. So something I want to really communicate to the students, because you probably do hear it all the time, and you think, I didn't get into engineering to write reports, right? I didn't get into engineering to be a communicator. But the reality is that you are going to need to figure out how to communicate complex topics to a very diverse set of stakeholders. I think my very first presentation I gave when I joined MITRE was based on some of my graduate work that we were hoping to use. And I got to the end of it and they were like, too many equations. And so I said, okay. The pilots were like, I have no idea what you're talking about. And so I learned kind of quickly that I have to shape the messaging. You know, sometimes I don't need to tell them all the details because that's not what I need them to take away. So really thinking about what you're trying to get out of a discussion. So you really do need to learn effective communication through your technical writing, your presentations, briefings, and even how you communicate to folks via email. And what I've learned is often less is more. The other thing I've learned is almost nobody gets it on the first time you've told them. And so I think the rule of thumb is you have to tell somebody something 7 times before they kind of internalize it. And so we do use this at work quite a bit to remind ourselves, okay, we need to repeat this discussion and not be frustrated that they don't know what we're talking about just after one discussion. So think about that. I mean, I think that will help make you an effective technical leader in your field is effective communication. So the other challenge is this increasing reliance on automation. I think when we think about modernizing things, we often think about more automation is where we want to go. And we need to do that with caution. We need to proceed with caution. And so while these future documents do talk about an increasing reliance to aid decision making and automate some tasks and provide some real-time monitoring of operations, we do need to think about how that evolution happens to ensure both trust in the automation, but also to ensure those resilient systems when things potentially break down. So maybe at some point the automation stops working because you're in a a condition for which it wasn't designed. There is a researcher that has defined this autonomy conundrum, and just a quote from her: with increasing autonomy, robustness, and reliability, the lower the situation awareness and the less likely the human operators will be able to take over manual control. And I can tell you that air traffic controllers we work with, they express this, and I'm pretty sure they haven't read this technical paper, but they have internalized this, that if I don't practice taking over control, when I need to take over control, I'll be out of practice and something bad will happen. So this is something we have to think about when we're introducing new procedures or new automation, is how do we give them that comfort or trust in the automation, but also the awareness that they can step in if they need to recover the situation. So this gets into thinking about how do we smartly evolve automation in socio-technical systems. So can we develop these models to quantify what we call the robustness and the performance limits? So one, we have to think about how these systems are interconnected and effectively represent that systems integration before they ever get to the field. So that's got to be part of the testing. We need to understand those situations that might emerge that weren't predicted when we were just defining the systems. And there's really an opportunity to think about the validation process and how that needs to evolve. It can be challenging, especially when you have these human-in-the-loop systems, because obviously if you're testing them with humans in the loop, you're limited to real time. They definitely don't want us to speed it up to 1.5 times like you listen to podcasts. So, you know, that limits how much you can test the systems. But there are opportunities to test things in a fast time environment, and then perhaps more opportunities to find conditions with high performance computing, with AI tools that might help you define scenarios where you can find those situations. And then maybe that allows you to fine tune what scenarios you want to look at with humans in the loop. And then we talk about resilience. So we really need to think about this human machine teaming concept where the automation and the human are a team. How does the human maintain that awareness of the state of the system and step in, as we talked about? And then how do they recover from disruptive events? So we do need better requirements development and management. I think digital engineering is all the rage, the talk about how do we define things digitally so we can do digital twins to do this exploration. We're having all of those discussions at MITRE. The other topic that is a hot topic is how do we use artificial intelligence capabilities to improve human decision making. And so there was an executive order from the Biden White House on encouraging government agencies to explore the use of artificial intelligence in agency activities. And then the Office of Personnel Management put out a memo that further details responsible use of generative AI for the federal workforce. So this is a very specific flavor of AI. And so some of the key principles, as I think the FAA goes forward with exploring AI solutions, is that there's a recognition that they offer opportunities to improve efficiencies, but again, they should be seen as teammates to humans. I think we're a long ways from just accepting the AI solutions that come out of the machine without any checks, any human in the loop. We're also asking everyone to disclose the use of AI solutions, even doing this in our reports at work. So now we are starting to use generative AI for report editing, literature reviews, but we need to be honest about that. And then ultimately, at the end of the day, the humans are still responsible for ensuring accuracy, clarity, truthfulness, and objectivity. I think the concern about bias in AI solutions is ongoing, and I think there's work trying to ensure and test those generative AI capabilities for potential bias. But at the end of the day, the human is still responsible for passing through that AI solution. Another challenge, alignment of government and industry investments and timelines. So some of our solutions require FAA investments in infrastructure and automation, but also industry investments in aircraft or flight operations capabilities. And so this has really been a huge chicken and the egg problem. So industry sometimes says, well, I want the government to prove they're going to do something before I invest. And then the FAA will say, well, I don't know if anyone's going to invest in this, so I don't think we should invest in this either. And, okay, somebody's got to move. So a real chicken and the egg problem. You know, some of these systems have long deployment timelines. You know, we're not in the world of iPhones or you know, handheld technology that you might have for a year and then get a new one. Airplanes stay out in the field for 40 years, and they're very expensive to retrofit. And so it's challenging to upgrade fleet capabilities without a lot of confidence that those capabilities will be used. And so we do start to see cases for agile software development processes, service-based software architectures, and new aircraft certification processes. Right now, it's very expensive to open up, for example, a flight management system and add a new capability to the aircraft. And so can we figure out how to do that more cheaply? And in fact, it's frustrating because we're doing all this data analysis and we might find issues that we really want to fix, but they'll go unfixed for a long time because of the expense to fix them. If there's not a safety reason, we might not be able to fix them for a long time. So this is another challenge. There's a lot of question about how to balance the pace of technology and innovation with ensuring the safety of the American public. So I think, you know, corporations, I mean, they don't want to do harm, but often they don't have the big picture. And that is why, you know, sometimes they're saying, go faster, government, go faster. We have this great commercial opportunity we want to pursue. And the government's saying, we must be cautious. And in fact, they're often resource limited because they're being pulled in a lot of different directions. And so how do we effectively get industry and government to partner to both increase the pace of innovation, but make sure that we still have the best interests of the public in mind? And so there's been a lot of talk about public-private partnerships that provide a forum for sharing standardization and consensus building. I think MITRE is a great partner in doing that. We understand the processes of the government, but then we also can provide analysis support and bring together some of the industry stakeholders to understand what they're trying to do and balance all of those competing objectives. Standardization versus innovation is another one. So this gets into the idea of how much regulation is too much regulation. And so today we have standards in the aviation industry to ensure safe and consistent performance that achieves what were the operational objectives. And so, you know, aircraft capabilities, for example, variations in those can be really challenging for air traffic control. So when they say speed up or slow down or change your altitude, they do ultimately want aircraft to behave somewhat similarly, and they're amazingly good at understanding different aircraft performance and setting those expectations. But ultimately, we do want to get some consistency. And so we do, at the same time, need to balance standardization and innovation. So we want to give opportunities for commercial entities to innovate and provide a business case. But at the same time, what is that threshold for standardization we need? Obviously, if we're sharing information, those formats have to be specified. There's certain things that will just have to be done to make things work. So finding that right balance of standardization and innovation is a challenge we deal with as well. So now I want to talk through a few specific project examples. I'm going to talk about some projects that I myself have been heavily involved in, but also a few highlights of other work that MITRE's doing that are really important aspects to modernizing the system. So in terms of addressing legacy air traffic demand, I've worked for my entire career, the 15 years I've been at MITRE, on a concept called interval management. So you could think of it as an automatic cruise control for airplanes concept. And it leverages the automatic dependent surveillance broadcast technology that is now mandated for all aircraft operating in certain classes of airspace in the national airspace system and actually worldwide. So the idea is that the trailing aircraft would implement speeds that achieve and maintain a spacing interval relative to a lead aircraft. And the idea is that this improved spacing precision allows you to pack in more aircraft over a point or at a constraint or at an arrival airport than you would without this precise spacing. So we've worked on this for many years. We've developed avionics standards, we've done algorithms, we've done testing, we've done human-in-the-loop experiments collecting data on pilots and air traffic controllers. And over the last 2 years, we've had an operational evaluation, the ADSB and retrofit spacing evaluation with American Airlines. And so they've equipped all of their A321s, which is over 300 aircraft, with an avionics package. It is kind of an early generation avionics package. We've had 2 years of data collection in Albuquerque en route airspace. So Basil, if you're flying in on an American Airlines A321, maybe there's a chance that you're doing an interval management operation. You shouldn't feel it. If you do, let me know. And so what we found is that 90% of those operations were within 10 seconds of the spacing that they were told to achieve. And if you compare that to similar, American Airlines flights that weren't doing these operations, only 23% of those were within 10 seconds of their goal. So it's really exciting. This has been, well, probably the thrill of my career. The American Airlines technical pilot we work with said, "It's what Leslie's been telling us." And I said, "I don't know why you didn't believe me," but it's really gratifying to see the real world data. And we're getting the data cards off the aircraft, and so we have just copious amounts of data. The reports for the first year of data collection should be public soon. They'll be on the FAA website, so you could probably Google them and find them soon. So this has been a really exciting outcome. Another project that I worked on recently was looking at integrating space launch and reentry operations with legacy air traffic operations. And so the problem, of course, is that as we have more and more launch sites and launch tempos increase, we do need a flexible and scalable traffic management approach. So what they do when there is a launch planned is there's an analysis to determine the region of airspace that needs to be closed. It's called the aircraft hazard area, and that protects the legacy traffic or other traffic not involved with the launch from a launch failure, from the vehicle itself, and if there is a failure and there would be a debris field. So it's a very large area of airspace that can be closed. And depending on where that site is, it can affect quite a few flights. So what we were trying to do is determine how well you needed to predict the aircraft trajectories intersecting with that aircraft hazard area, such that you could effectively determine which ones you want to maybe reroute or delay so that they wouldn't intersect with that hazard area or they'd be out of the hazard area in time. And so we did an analysis on this. We recently published a paper in the AIAA Journal of Air Transportation, and we came up with a requirement that says, here's how accurately you need to predict your trajectories for the aircraft so that you can effectively manage them. And the good news was that one of the FAA's new traffic flow management platforms accepted the requirements, so they're going to build a trajectory modeler that meets these requirements, and so we can start to build decision support tools that support this objective. So little wins. This was a mathy one. We had fun with this one. Another project I'm leading is integrating advanced air mobility operations into the National Airspace System. So obviously this is a hot topic. I'm sure you're hearing about it. It is a priority for the Department of Transportation and the FAA. And the 2024 FAA Reauthorization Act has several sections that refer to the U.S. Leadership in this area, that the U.S. should lead in integrating these operations into the NAS. So one of the ways that we're going to support these operations is this extensible traffic management concept, where third-party service providers can assume some of the traffic management responsibilities, so it doesn't have to be air traffic control managing them. And then the operations themselves will be defined by something called the cooperative operating practices. So this says what the fleet operators need to do in order to conduct their operations. And so there's not a lot of details on this right now. The FAA will be responsible for approving those operations. And so the research we're doing right now is understanding how these cooperative operating practices will be developed and evaluated so that you can ensure there's fair, equitable, and efficient operations. Given this multi-stakeholder environment, you might have multiple fleet operators operating in a region, you might have multiple service operators. So how do we make sure it's fair? So we're doing a lot of modeling and simulation to kind of represent some notional ideas of cooperative operating practices in a modeling environment. And we'll have a paper at AIAA SciTech in January that details some of this work, getting into all the detailed optimization. math. An area where I'm touching on, but I'm not doing any major leadership in, is this automation evolution strategy. I mentioned moving to cloud-based environments from kind of legacy software and hardware implementations. And so MITRE is working with the FAA to define the strategy to modernize software development and deployment. Talk about cloud-based systems, so you can imagine what some of the big challenges there are around cybersecurity. But the idea is that you could reduce the cost to develop, operate, and sustain these systems. And then furthermore, instead of having big changes to systems that are really hard to introduce to the humans, going back to talking about the acceptance of changes, the idea is to do smaller incremental changes. It's more of an evolution rather than a revolution. And then this starts to get into industry best practices for software, but also wanting to promote competition between vendors. So instead of having one vendor that designs this multi-billion-dollar system, individual vendors could come in and design smaller functions and deploy them in the software architecture. We talked a little bit about use of AI and machine learning capabilities, so we do have research in this area. So some of it is around proposing traffic flow management solutions to human decision makers, so training models on past decisions, past data. An organization or a group within MITRE is working with the Aircraft Certification Organization to develop certification guidance for machine learning algorithms. So of course you can imagine the starting point is not that you would have online learning and the system would be evolving, but rather you develop a machine learning static algorithm that you can test and validate. So that is the starting point, but working with the FAA to support that. Lots of use of large language models to process air traffic logs. So these are human-entered text that is difficult to mine if you're just using traditional kind of search methods. And so LLMs offer a new opportunity to pull information from lots and lots of recorded data, also voice data. So lots of voice-to-text transcription, which then can be mined for findings. And then we're even looking at use of large language models to improve FAA business processes. So where can we help the FAA be more efficient? And then lastly, another area that we're starting to work in is in high-speed flight. And so in the 2024 FAA Reauthorization Act, it's one of the first times they mention supersonic and hypersonic flight, maybe in a long time, maybe ever. I don't have enough history on the reauthorizations, but I should say the FAA Reauthorization Act is what authorizes the FAA to serve in its role, but then also provides direction. And so this section on high-speed flight talks about supporting flight testing, integrating these operations in the NAS, and enabling these operations in upper altitude airspace. And so MITRE is working with the Midland Development Corporation in Midland, Texas, which has several companies and industry in that area that's interested in high-speed flight. There's a company called Starfighter Space, which is F-104s that they're flying. They want to launch satellites from those aircraft. And then Firehawk Aerospace is also interested in building propulsion systems for high-speed flight. And so the goal is, this is a multi-year agreement to work together to accelerate this vision for commercial and high-speed flight operations. And this is also, I'll note our AIAA partners on this as well. They're also working in this area. And so having a lot of conversations about what work needs to be done and how can we support the community. So thank you for bearing with me during all of those challenges, but I hope what you take away is not that there's insurmountable challenges, but rather there's a lot of exciting stuff happening right now. And also, I think so often, people don't think of the FAA as a super challenging organization. I think NASA gets a lot of the credit for doing cool stuff. But I'll say that, given the complexity of the NAS, it has to operate 24 hours a day, 7 days a week, 365 days a year. And you already see how many humans are in the loop in that. It's a really challenging environment. There's great opportunity to solve technical problems, technical challenges. I did want to tell you about some of those other challenges that make the problem more complex, but maybe more exciting. And so I wanted, as the future workforce, the students in the room wanted you to think about this big picture. It does affect the pace of innovation and technology evolution, for human acceptance across a lot of different stakeholders. So these big pictures really do affect what we can get done and when. So before I close out and take any questions, I did just want to note, Basil did talk about our, how we met, well, at Texas A&M, but got to know each other more through AIAA. AIAA has been huge for my career. And it's interesting as I've gotten into a leadership role and AIAA is trying to look at some of these big challenges, the intersection with my day job and my volunteer job sometimes gets blurred. And it's really beneficial to me because I'm learning all these new areas that I hadn't touched before and learning about these kind of interdisciplinary challenges. So I did want to just encourage the students to think about professional society membership. I know we have mechanical students here too. Maybe AIAA is not the right professional society for your interests, but really think about that and how it can be a way to do continuous learning, and think about how you could take on leadership opportunities as part of your career development. So I wanted to put a plug in for that, as it's been really impactful for me. And with that, I would love to take any questions you have, and thank you so much again for the invitation and for the opportunity to talk to you today.
I don't know if it's working. Yeah. Christian, you talked a little bit about like the hurricane relief and the air traffic control with that. With the hurricane that recently happened to West Carolina, I don't know if necessarily you had anything to do with it, but what was the process of the air traffic control in that area with all the cell towers out? How did you guys get communication in, and kind of how did you go about the ground support as well?
So I definitely am not an expert on how they, how they managed recovery from the hurricane. I'll forecast information several days out. And I think a lot of that is more, planning to make sure that airlines are making decisions about where aircraft will be, what flights need to be canceled, being proactive about it. I don't know if there were long-term kind of surveillance implications for managing air traffic. Right now, with ADSB, I mentioned that is a satellite-based navigation system. So there's ground stations that get that data to air traffic control, and there is overlap, and they have a decent, I don't know what the range is for many of them in terms of when they can receive the data, but I don't recall there being a long-term outage in terms of when they could manage air traffic in that region. So I think that was not an issue, but planning for it in advance, they would have been looking at weather forecasting and trying to make decisions. So, thanks.
And question a little about mobility. Some of your thoughts on in cars, this kind of application.
So obviously there are some of the eVTOL companies are making great progress with developing and certifying and getting airworthiness certification for their aircraft. And so I think that I do expect the timelines that they're advertising for when they could start operating are for some of them are probably pretty reasonable, those that are further along in their development. I think there will be some early operations that can use current regulations, current procedures, and so those will be at lower density operations. So I think we will see some eVTOL, advanced air mobility operations in the not too distant future. I know the FAA has a Innovation 28 plan, I think, for Los Angeles, and you can imagine that intersects with the LA Olympics. That's a great showcase for some new technology and innovation. Some of the work that I talked about is really starting to get into those higher density operations where you need additional automation systems to help deconflict and manage the different fleet operators. That will be a longer timeline. And I think part of the uncertainty right now is that we don't know just commercially what the demand is going to be for those operations and how quickly they could potentially grow. I think there's still a lot of questions about the scalability of the manufacturing as well. So there is a lot of uncertainty. We're trying to be proactive, but it's difficult just given the amount of uncertainty right now. But I do think we'll see some early operations. In terms of like UAS, that's a little bit of a different operation. Those are mostly happening under 400 feet above ground level. So there's activity happening now in Dallas with unmanned aircraft system stakeholders that they are doing some early operations. They have letters of agreement between all of the stakeholders there. They're learning quite a bit. And so those operations have started, and those are beyond visual line of sight operations too. So I believe most of them are still remotely piloted, but you don't need to have visual line of sight. So there's progress being made in all of these areas. So it's just, there's a lot of questions about scalability. And, you know, as the Dallas area learns, you know, how quickly is it to start those operations in another part of the country too? That's something we're thinking about as well. You know, if you have a set of stakeholders and now you have to start that over again, how quickly can you take the lessons learned from Dallas and apply them somewhere else and get those operations stood up? So, thanks.
Thank you. Talk, and especially the talk about automation and how to not get too caught up in it that if something fails, we don't know how to recover. So are you folks working on what will happen if there is some unanticipated GPS? Because it seems like everything nowadays is pilots, air traffic controllers, everybody is now becoming more and more dependent on GPS and getting trained on that to the point that we don't get practice with other approaches.
Yeah, so MITRE is doing work on navigation resilience. So looking at leveraging some of the legacy navigation aids that you might need to revert to if there is a GPS failure or GPS outage. It is interesting because, you know, I would say probably a couple decades ago, the idea was we're going to move to GPS and we can divest from these legacy systems. And I don't think that's the vision anymore. The question is, what is the minimum set that we need in place so that we can effectively revert to that prior solution? And again, it's an efficiency loss because the navigation is less accurate. You might have to, you know, stem some of the demand, but it's safe. And so there is a lot of work on that right now. And I just saw an article that Finland is reverting to some of those legacy navigation aids because of GPS interference. So I think we're not the only country that's looking at that and considering that. So. Yeah, so I'm not an expert in that area. I will say some of MITRE's early work in that is starting to look at what is the airspace design that would be needed to allow flight testing to happen, for example, between the Midland Spaceport and Spaceport America in New Mexico. So is it a corridor? How dynamic does that need to be? Also looking at things like what's underneath that from a noise interference perspective. Even national parks, you know, how disruptive is it to have a sonic boom over your national park? So that's some of the early work that MITRE's doing, which really gets to that integration into the national airspace. And then also looking at the interference, any potential interference with legacy air traffic if they did set up that testing corridor. I don't know enough about how the FAA is reacting to that section. They might still be processing what that means. I do know that they're working with other groups. So of course NASA is doing a lot of work around aeroacoustics and the sonic boom mitigation. And so I think the FAA is certainly monitoring that work. But unfortunately, sometimes what's in the reauthorization, they'll call it kind of an unfunded mandate. And so then it's kind of figuring out what can we get done in this area. So this is really a fortunate partnership that actually started before that reauthorization language came out. So hopefully we can leverage what we're learning for that with the FAA. But unfortunately, I can't speak in more detail than that. So.
All right, thank you. Give a round of applause for Leslie. Something to remember coming to NC State. This is somebody can take a picture. I think Jack will come down and take an official
Jack
picture.
is doing everything. Thank you.
Anybody, you want to take a picture quickly? With your phone? Come on. And come in. You need to come anyway.
All right.
Somebody take one picture and just send it to me.
Thank you. A swag bag? Thank you so much. Thank you. Thank you so much. Thank you. Thank you all for attending. This is the what next one is next year. We'll announce it soon. I think Basil always has ideas on who to invite. So look forward to having you all again. Thank you. Thanks so much.
That's a lot of stuff.
Very cool. I know, right? Well, hopefully.
So I didn't ask the question because I said urban air mobility because under 400, but still a complicated problem.
It is, and there's going to be, I mean, especially as the number of operations scales, they will have these third-party service providers supporting that, and there's going to be standards and whatnot, but yeah.
Oh, I have